In this example, we are going to delineate urban areas using the proposed methodology of the MaiL project. Urban areas are defined using a combination of the Korean land cover dataset and the high-resolution imperviousness layer. As you can see, the Sentinel-2 Global Land cover product contains also information about urban areas. However, the comparative analysis of these three different datasets indicated that the Korean land cover product and the high-resolution layers are representing urban areas more accurately. So in this case, the Sentinel-2 Global Land cover product was excluded from further analysis. The proposed methodology will be applied in one of the pilot cases of the MaiL project, and more specifically in the suburban forest area of Kedrinos in Thessaloniki, Greece. The area consists of several potential sites that could be defined as marginal lands, including semi-urban degraded lands and low productivity lands adjacent to natural parks and forest areas. To begin with, first download all the required datasets from the corresponding data repositories, or you can use the geodatabase of the MaiL project. We will need the following layers: the Korean land cover dataset and the high-resolution imperviousness layer. Open the Qgis application and create a new project. We recommend using the latest version of the application. To begin with, first we have to create a new shapefile layer containing the area of interest we want to apply the proposed methodology. To do so, it's better to first add the base map in our map area. Go to Web, select Quick Map Services, and here you can see all the available options to add a new base map in the area. Select Google and add Google Satellite. Now you have to locate the wider area of interest. We navigate towards Thessaloniki, Greece, and here you can see the wider area of Kedrinos. Now we are ready to create the new shapefile layer. To do so, first we need to open the catalog tree of the Qgis application. We select View, Panels, and we click on Browser, and this is the catalog tree of Qgis. Now we have to locate the desired directory we want to store the new layer. Right-click on the desired folder, select New, and select Shapefile. A new dialog box appears containing all the options to create the new layer. First, we need to name our new layer. I choose to name it after as Thessaloniki AOE. We leave the file encoding as it is by default, and now we have to define the geometry type of our new attributes. In this case, we need to create a polygon containing the area of interest. Right-click on this icon in order to define the coordinate system of the new layer. A dialog box appears where we have to identify our projection. Within the context of the MaiL project, all data are referring to the European grid projection. This projection is identified using the EPSG code 3035. Once we filter this number here, in the predefined coordinate reference systems, a new list appears where we can see the corresponding projection, and we choose the ETRS 89 Extended LAEA Europe. Click OK. Moving on, the new field dialog box contains the options to create a new field in the shapefile. That is a new field column in the attribute table of the shapefile. In this case, the default field contains only the ID number of each attribute polygon we are going to add in our layer. We can add also any other information we want to appear in the shapefile. For the moment, we leave it as it is by default and we click OK. Now it's time to add this new shapefile in the map area. We can either drag and drop the corresponding file on the map or use the available toolbox. In this case, select Data Source Manager and then select the data type vector. In the source box, navigate to the location you have saved your shapefile, find the new layer and add it to the map. As we can see, we can save it on File, MaiL, and that's the Thessaloniki AOE, and add it to the map. And this is the new layer appearing here in our Layers panel. To explore the attribute table of the new shapefile, right-click on the layer and select Open Attribute Table. As you can see, the shapefile is still empty as we haven't added any polygons yet, but we can see the default field ID. Close the attribute table, and now it's time to draw a new polygon in the shapefile. First, we need to activate the edits on our layer. To do so, click on the option Toggle Editing. Now the layer is active and we can draw a new shape. To add a new polygon, click on the option Add Polygon feature. Navigate to the map and draw the desired shape containing the area of interest you want to apply. To complete the shape, right-click on the last point and a new dialog box appears to complete the field of the new polygon. Fill in the numbers of the polygon with the value 1 as it is the first polygon in the shapefile. And finally, save your edits. Now you can see the new polygon area appear in the map area and the corresponding field in the attribute table. Finally, you can modify the appearance of the shape by right-clicking on the layer and select Properties and Symbology. As you can see, there are several options to modify the new shape. This procedure was used to create a new polygon for the area of interest. In any case, you can also utilize any other available shapefile to define the area of interest. Moving on, we need to add to the layer panel the remaining datasets. Let's start with the Corinne land cover dataset. The Corinne land cover is available as a geopackage format, which is a way to store a database container on QGIS. Open the Data Source Manager and select Geopackage. Click on New to create a new connection. Navigate to the folder of your data and select the corresponding land cover dataset. Click Open and click Connect. Once you do the connection, in the following table we can see all the available geopackages contained in the folder. Click on the first one and select Add. The polygons of the Corinne land cover are now added to the map area. For the moment, the layer is added using a common symbol for all the different polygons. In order to see the different land use categories of this dataset, we need to modify the symbology of the layer. Right-click on the layer, select Properties and go on Symbology tab. Now, change the single symbol into Categorized. In the field Value, we need to select the value that will be used to classify our data. In the case of Corinne land cover, the value of each class is assigned to the value code 18. Select this value and in the layer rendering style, select Load Style. Select the option from File and navigate to the original data folder. As you can see, a separate folder called Legend is included in the original data. Load the corresponding QGIS layer settings file, open and load the style. The symbology style is now applied and the legend of the new layer represents its different land use category with different color in the map. Click Apply and OK. Finally, we need to add the high resolution imperviousness layer. Open again the Data Source Manager and this time select the Raster tab, as this layer is a raster image representing the percentage of soil sealing. Navigate to the source of the data and select the corresponding raster tile of this dataset you need to add to the map. In the case of the Thessaloniki case study, we need the tile in the area East 54 and North 20. So select the corresponding tile and import the TIFF image. Click on Open, Add, Close, and the layer is added to the map. Now that we have loaded all the essential data, we can start the main process for the delineation of urban areas. First, to speed up the process, we recommend clipping the extent of each dataset to the boundaries of the area of interest. This action can be performed using the corresponding clipping tools for vector and raster layers respectively. Let's start with the vector Corinne land cover dataset. Go on the processing toolbox, select Vector Overlay and clip. In the input layer, add the Corinne dataset. The overlay layer will be the extent of the area of interest. You can either create a temporary layer and save it afterwards, or you can directly save the file in a shapefile format. Let's choose this option, Save to File, and name it after Corinne Clip. And now you can run the process. As you can see, the Corinne dataset is now extending within the boundaries of the area of interest. To adjust the symbology, you have to repeat the same process we performed previously and reload the corresponding QGIS setting file. Categorized, value code 18, style, load the style from file and select the corresponding layer. Apply and OK. Now let's clip the corresponding high resolution layer. From the GDAL toolbox, select Raster Extraction and clip Raster by Extent. The input layer will be the corresponding IMD high resolution layer. The clip in extent will be calculated from layer and more specifically the area of interest. Now we are going to save the new clipped image into a new TIFF file. Select the location of the file and select IMD clip, let's say version 1. And now run the process. As you can see, the high resolution layer now is extending within the boundaries of our area of interest. Let's return on the Korean land cover dataset. In this case, we need to extract all land categories representing urban areas. As you can see the legend, classes starting with value 1 are representing the impervious urban areas except for classes 131 and 132, which are referring to mineral extraction sites and dump sites respectively. These two land categories are excluded from the analysis. First, open the attribute table and notice that the land use categories are assigned in the field code 18. Now go to the processing toolbox, select vector selection and extract by attribute. As you can see, the input layer of the Korean clipped vector is already assigned. Now it remains to select the expression we are going to build. We already identified that the field code 18 refers to the class categories. So in the list field and values, select code 18. In order to include all urban areas, we need to assign a new operator in our expression. This operator from the corresponding list will be the in. In this case, we say that from the field code 18, include all values, and now open a bracket, and start typing all field values assigned to the categories representing the urban areas. Don't forget the quotation marks and the separator comma between the values. So it's 111, 112, and go on until you finish with all the values. Once you have completed the process, close the brackets. The brackets will turn green if the expression you are using is valid with no errors. Click on OK, and now you can see the expression you have created in the corresponding box. In the field matching features, we are going to save the file with all the features matching the expression we have created. In this case, this file will refer to all urban areas. Finally, there is an alternative option to save the non-matching features, that is the inverse results of our expression. In this case, a separate file containing all the remaining non-urban areas will be created. So save to the file these two corresponding images. Let's say Korean urban and Korean non-urban. Run the process and close the window. And now you can see two separate files that have been created. Let's focus on the Korean urban and see that we have now created a layer containing only the urban areas within our area of interest. To reassign the symbology, just load again the proper symbology file. Go on Properties, Symbology, Categorized, and load again the style. So now, with this way, as you can see, according to the information, here in this file we have only the Korean land cover urban areas within the area of interest. And this is the extent of our impervious areas according to this dataset. In the case of high resolution layer, a similar approach will be applied. In this case, according to the documentation of this layer, all pixel values greater than 30% are representing impervious urban areas. Moreover, values equal to 255 are assigned to no data values. So, we need to create a new layer that will contain only the pixel values representing impervious urban areas without including the no data values. To extract these values, go to the processing toolbox, select Raster Analysis and Raster Calculator. A new dialog box appears where we are going to build the new expression. As we already mentioned, from layer IMD clip, we need all values greater than 30, and from the same layer we need also all values which are less than 255. The reference layers used for the automated extend, cell size and the coordinate option will be the already original IMD layer we have clipped. Also, the output extend will be the same with the original file, and the output coordinate system will be the system we are working, the EPSG 3035 European grid. And now let's save the new file permanently, and we can call it as IMD Urban version 1. And now run the process. The results of the analysis is a raster image containing two values, where 0 values are indicated no data or no urban areas, while values assigned to 1 are all urban areas. This raster layer represents the extent of impervious urban areas according to the high-resolution dataset. At this point, we have created the impervious urban areas layers using two different data sources, the high-resolution urban areas and the corresponding Corinne urban areas. To combine these two datasets, we need to convert the Corinne land cover vector layer into a binary raster image. First, open the vector layer and activate the edits. Open the attribute table and select all polygons. Go on the edit and click on the merge selected features. Click OK, and now save the edits. As you can see, all urban areas according to this dataset are now represented in a single polygon. Before rasterizing the layer, we need to create an additional class representing the non-urban areas within the boundaries of the area of interest. To do so, we need to union the two vector layers, the Corinne urban cover dataset and the Thessaloniki AOE extend. Go to Overlay Vector and select Union. The input layer will be the Corinne clip urban areas, and the overlay layer will be the Thessaloniki AOE. Save the new union file and run the process. The new vector layer contains one polygon representing urban areas and one polygon representing all non-urban areas. Rename the object ID of these two different polygons. First, make this layer editable and give values 1 for urban areas and 2 for non-urban areas, and save your edits. Now we are ready to rasterize the new vector layer. From the processing toolbox, go to GDAL toolbox and select vector conversion, and then the option rasterize vector to raster. A new dialog box appears where, as an input layer, we will use the new union shapefile. In the selection field to use for a burn-in value, we select the object ID. The output raster units will be the units based on our projected layer, so we choose the option georeferenced units. The horizontal and vertical resolution will be 10 meters respectively, and the output extent will be the extent of the original shapefile. Finally, set the output data type into unsigned integer 16 to speed up the process and save the file. Let's say Corinne raster version 3. And run the process. The final result is a new raster file containing the original values as classes. That will be 1 for urban areas and 2 for non-urban areas. Finally, to reclassify the raster in order to have the same classes as the high-resolution layer, we will use again the raster calculator. Go to Raster Analysis and click on the raster calculator. The raster calculator returns always a binary raster containing a class with values equal to 1 for the areas that meet the requirements of the expression and 0 for all other values. So this time, the expression will be extract all values from the Corinne raster, which are equal to 1. The output, the reference layer used for the automated extracted cell size will be the one of the imperviousness layer. The cell size, the output extent will be the extent of the original layer, and the output coordinate system will be the European grid. Save the new file, Corinne reclassify, and run the process. Finally, we have two different datasets, raster datasets, containing now the same classes, 0 for non-urban areas and 1 for urban areas. The final step includes the combination of the two raster layers using a Boolean function. In this case, we are going to implement the function raster Boolean OR. Go to raster analysis and select the corresponding function. In the input layers, include the two classified images according to the Corinne land cover dataset and the high resolution layer. So we use the Corinne land reclassify and the high resolution layer, and click OK. This algorithm will calculate the Boolean OR for the two datasets. In this case, if any of the input rasters have a non-zero value for a pixel, that pixel will be set to 1 in the output raster. Otherwise, if all the input raster files have 0 values for a pixel, this will be set to 0 in the new output raster. As a reference layer, we are going to use the high resolution impervious layer. Save the new raster image and apply the function. We can set it as impervious version 2. The final raster layer represents now the urban impervious areas based on these two different data sources. This layer is the intermediate layer impervious and can be utilized in the final workflow for identifying the layer of marginal lands based on the hard thresholds approach. Thank you for your attention.